Okay, so in the last set of lectures, we started off by introducing to the concept of creep, and then I talked about the importance of studying creep, and following that we talked about the basics of plastic deformation. Since creep is a plastic deformation process, so it was important to touch upon a few concepts of plastic deformation. And since plastic deformation in general involves the motion of dislocations, so we also discussed about some characteristics of dislocations. And in today's class I will take you into more detail on creep. So, we will go into the concept of creep and discuss it in greater detail. So, today's class is about introducing you to creep, and then gradually we will talk about the different factors that influence creep deformation. So, so basics of creep and the different factors that influence creep deformation. So, like I mentioned in the first class, creep is a time dependent plastic deformation process that happens in a material experiencing a constant load or constant stress condition in the presence of a temperature. Typically, the temperature has to be fairly high. It should be at least 0.4 or 0.5 times the melting point of the material. Now, the tests that we do at a lab scale are usually at constant stress, but in real life materials usually fail under constant load conditions. So, materials creep as well as fail in real life under constant load conditions. However, the need of carrying out creep tests at constant stress comes from the fact that it becomes easier to analyze the creep data when the tests are carried out under constant stress. So, the data that is generated will be analyzed better, as well as it becomes possible to understand the rate controlling mechanisms of creep deformation when the tests are carried out at constant stress. Having said that, it is not that tests it is not that tests nobody studies creep tests under constant load. There is a lot of work that happens on there is a lot of work that happens where people study the creep behavior of materials under constant load conditions. Now, creep is generally described by plots of strain versus time. So, a typical creep curve is described by plot of strain versus time, where strain is on the y axis and time is on the x axis. Like I mentioned, the creep curve is a result of a test carried out under constant load or constant stress at a constant temperature, and the strain is recorded as a function of time. So, this is how a typical creep curve looks like. So, you have 3 stages marked as 1, 2 and 3, and the first stage is known as the primary creep stage, the second stage is known as the secondary creep stage, or also known as the steady state creep stage, and the third stage is known as the tertiary creep stage. So, in this plot I have delineated the 3 stages using these dotted lines. So, the nature of the creep curve that you see here could change depending on the mechanism in operation. There are different mechanisms that have been proposed to explain creep deformation, and depending on the mechanism that is controlling creep deformation, the nature of the curve could change. For example, here is a curve where the mechanism, the curve in blue is a result of creep deformation being governed by another mechanism. So, let us call it mechanism 2. So, the first curve, that is the curve in brown, is a result of mechanism 1, and the curve in blue is a result of mechanism 2. And if you see, there is clearly a difference between curves produced by mechanism 1 and curves produced by mechanism 2. We will elaborate in detail, I will elaborate in detail during the subsequent classes why there is a change in the creep curve, but the main point or the bottom line here is the nature of the creep curve by itself could also tell you if a one type of mechanism is in operation versus another. So, here what we observe is stage 1 is actually very small when the creep curve is progressing by mechanism 2, whereas stage 1 is large when the creep curve is evolving because of mechanism 1. So, the nature of the creep curve also provides us insights into the deformation process. So, we talked about 3 stages of creep: stage 1, stage 2 and stage 3. So, the first stage, also known first stage of creep, known as the primary creep stage, is generally characterized by a decreasing strain rate of deformation, and the second stage or the steady state creep stage is characterized by a constant strain rate of deformation, and the third stage of creep, known as tertiary creep stage, is characterized by an increasing strain rate of deformation, eventually leading to failure. These are the 3 stages. So, generally whenever the material is loaded, what has been observed is there is always an instantaneous elongation on the application of the load or stress. So, only after the material has undergone this instantaneous elongation or instantaneous strain, it is only then that it enters into the primary creep stage. So, this is how a creep curve would look like. You have an instantaneous strain, and then you have a primary creep, secondary creep and tertiary creep stage. So, this instantaneous strain generally is represented by epsilon naught. So, the instantaneous strain epsilon naught it has been observed that the instantaneous strain epsilon naught is produced even at applied loads lower than the yield strength of the material, and most of this strain is recoverable upon the release of the load or stress, and hence this strain has an elastic component. So, epsilon naught is not entirely elastic. If you compare the creep curve to a stress strain curve, in a regular stress strain curve, you have an elastic region, a plastic region, eventually leading to failure, and this elastic region is entirely recoverable when the load is released. In the case of a creep curve, the instantaneous strain epsilon naught is not entirely elastic. So, epsilon naught has a part or a component which is elastic. So, let us say we call it epsilon naught is equal to epsilon elastic, and which is recoverable on the release of the load. There is another part of epsilon naught which is recoverable, but not instantaneously. This strain is recovered over time, and hence it is anelastic. So, let us call this epsilon A as anelastic. Typically anelastic materials are so materials which exhibit high anelasticity are polymeric materials, where the plastic strain is recovered once the stress or load is removed, but the recovery happens over a fairly long time. And the third component of the epsilon naught is non recoverable, and this is the part which is plastic in nature. So, epsilon naught will also have a plastic strain component epsilon PL. So, the epsilon naught consists of 3 items. You have epsilon elastic, which is recoverable on the removal of the load immediately, and epsilon anelastic, which is strain that is recovered after the removal of load, but the recovery happens over a certain period of time, and then you have epsilon plastic, which is strain that is not recovered on the removal of the load. Generally, for the purpose of analysis, people in the scientific community, they generally subtract the instantaneous strain from the total strain, and that is why since the instantaneous strain is subtracted from the total strain. So, that is why when you have plot of epsilon versus T, the creep curve generally starts from the origin of the coordinates. So, the creep curve starts from here, that is because epsilon naught is generally removed from the total strain. So, the creep curve we talked about 3 stages: primary, secondary and tertiary, and we also said the characteristic of primary creep is that there is a decreasing strain rate of deformation in the primary creep stage. In the secondary creep stage you have a constant strain rate of deformation, and in the tertiary creep stage you have increasing strain rate of deformation leading to failure. So, this can be understood better if you make a plot of strain rate versus strain or strain rate versus time. So, the same creep curve So, if you take the data from this creep curve and if you plot, if you determine d epsilon over dt, that is what strain rate is. So, if you determine d epsilon over dt and if you plot d epsilon over dt versus epsilon or d epsilon versus or epsilon dot versus time, then that is the nature of the curve, that is how the curve will look like. So, clearly in stage 1 the strain rate is decreasing, it attains a constant value in the second stage in the, that is the steady state creep stage, and then it continues to increase after the steady state. In the tertiary creep stage the strain rate of deformation continues to increase, and the same behavior is observed in both epsilon dot versus epsilon and epsilon dot versus time plot. The average value of the creep rate in this stage, the average value of the creep rate during steady state creep is also called the minimum creep rate. That is because as evident from the picture, the creep rate decreases, and once it reaches the steady state it more or less stays constant, and as you can observe from this figure, this strain rate is the lowest in the entire plot, and that is why this strain rate is also called the minimum creep rate. The creep curve in general can be considered as a result of a competition between mechanisms of strain hardening and recovery. So, the creep curve that we observe, the nature of the creep curve can be considered to be the result of a competition between mechanisms of strain hardening and recovery. So, there is some competition that is going on between strain hardening and recovery, and that is why the creep curve has the following form. Of course, this concept that there is some form of competition going on between strain hardening and recovery is largely applicable to the first stage and second stage, because in the third stage, that is in the tertiary creep stage, the material behavior is significantly different than that compared to in stage 1 and stage 2. That is why this concept of a competition between strain hardening and recovery is generally not applicable to stage 3. So, now coming back to this concept that there is a competition between strain hardening and recovery, in the primary creep stage the rate of strain hardening is higher than the rate of recovery. So, the material is strain hardening, and because the rate of strain hardening is higher, that is why the strain rate of deformation is coming down. So, the material is slowly, the rate of deformation is coming down, the strain rate of deformation as strain progresses. As we know, when a material deforms plastically there is strain hardening. So, because of strain hardening the material is becoming harder to deform further, and that is why the strain rate of deformation, that is epsilon dot, is coming down. But this is gradually balanced by the rate of recovery, and when the rate of recovery is equal to the rate of strain hardening, then you enter into the secondary creep stage. If there was no recovery process, then what would have happened is the strain rate would have eventually become equal to 0 or very negligible. So, the decrease in strain rate will continue to happen if there is no recovery, and the decrease will happen to a point where the material stops deforming altogether or deforms at so slow a strain rate that it is not even perceptible. So, since this is not happening, since we have a steady state of creep rate, that means there is some form of a restoration that is happening, and that restoration is the rate of recovery. So, in the secondary creep stage, the rate of strain hardening is balanced by the rate of recovery, which helps the material to continue to deform, plastically deform. Like I said, unlike the primary and secondary creep stage, the tertiary creep cannot be simply understood as a competition between strain hardening and recovery processes. That is because in tertiary creep or during tertiary creep, there is an effective reduction in cross sectional area of the sample, especially so if you are carrying out tests in tension mode. So, if your creep test is being carried out in tensile creep mode instead of compression creep mode, then you will see tertiary creep brought about by an effective reduction in the cross sectional area. The reduction in cross sectional area is because of necking, or for that matter due to internal void formation. So, as your material is straining, so let us assume a dog bone sample experiencing creep strain. So, slowly the material is going to extend and then this extension will lead to necking, and we know that during necking void formation can start happening locally within the material, and because of this reduction in cross sectional area or the formation of voids, the creep rate of deformation is accelerated. So, as the material starts necking or internal voids start forming, the creep rates are accelerated, and in addition to this these changes, there are also other metallurgical changes such as coarsening of precipitate particles or recrystallization or diffusional changes that the material could undergo in tertiary creep stage. Now, compared to a constant load test, the onset of tertiary creep is generally delayed in constant stress tests. The reason is, when you have a constant load test, so say you are carrying out a test under a constant load of P, so initial applied stress is sigma I is equal to P over A, but as the material starts necking or starts experiencing a reduction in cross sectional area, the stress acting at any point of time at any given location will be higher than sigma I. That is because for the same load, the new area A, let us call this A1, since A1 will be less than A, the cross sectional area A1 will be less than A, that is why the stress acting on the material sigma 1 will be greater than sigma I. So, what this means is, the material is going to enter into a tertiary creep region faster in a constant load test compared to a constant stress test. That is because in a constant stress test, you are going to change the load applied in order to account for the change in cross sectional area. So, in a constant stress test, sigma I will be kept constant, and that is done by sigma I is kept constant by reducing the load to P1 when the area of cross section has reduced to E1 A1. So, when the area of cross section has reduced to A1, you can reduce the load to P1 so that the stress continues to remain constant. But in the constant load test, that is not the case. So, that is why sigma 1 is higher than sigma I, and that is why you will reach the tertiary creep region faster in a constant load test. And also because of the reduction in cross sectional area and the increase in applied stress, the strain rate of deformation will also increase significantly. That is why the material will reach into tertiary creep faster. So, another aspect of this is, so the onset of tertiary creep is faster in constant load tests, and another observation is that the steady state creep stage or the secondary creep stage accordingly is also small or reduced. So, if you compare a constant load, a constant stress test. So, let us assume this curve 1 is for constant stress. So, curve 2 So, curve 1 is for constant stress and curve 2 is for constant load. So, what we observe in this case is the steady state creep region which was occurring over a certain time, say delta T1, is now reduced significantly. So, let us call this is delta T2. So, delta T2, that is the time range over which steady state creep is happening, is lower for constant load tests compared to delta T1, which is the time range over which the material is in steady state corresponding to constant stress tests, and the reason is because of the reduction in cross sectional area. Now, coming back to the creep curve being a result of a competition between strain hardening and recovery. So, this is a very interesting stage, because this gives you an opportunity to recall the concepts of strain hardening that we talked in the previous lecture. So, if you recall, we discussed strain hardening is a result of increase in resistance to dislocation motion. So, during plastic deformation, material experiences strain hardening, and the strain hardening is because of different mechanisms, such as it could be barriers to dislocation motion due to grain boundaries, or it could be barriers to dislocation motion due to solute atoms, or barriers to dislocation motion coming from fellow dislocations intersecting with each other, and things like that. So, that concept, those concepts are applicable to creep as well. So, as plastic deformation progresses during creep, the existing dislocations as well as new dislocations created during the deformation process move across the crystal, and they start intersecting other dislocations, or maybe they get stopped by other barriers such as grain boundaries or precipitates, etc. So, so you have in the grain dislocations moving, and maybe they encounter other dislocations, or maybe a better way of representing is this. So, if you have one line and then you have other line, and say the dislocation moves and then it intersects this dislocation, and we know what happens when two dislocations intersect each other. Breaks in dislocations are produced. These breaks could be jogs or kinks, and jogs on screw dislocations we know are difficult because they prevent the screw dislocation from cross slipping or moving easily. So, because of this process of dislocations moving around and intersecting with each other, a dislocation substructure is created. So, the dislocations are constantly arranging or configuring each themselves, because say you have dislocations, two dislocations that got intersected by another two dislocations. So, now you have some form of a mesh that is forming, and when you have multiple such dislocations, they are forming meshes. So, that is one example of a substructure that could form in the material. Now, because there is resistance to dislocation motion because of the strain hardening process, for further plastic deformation to happen, the dislocations have to overcome the barriers, and these barriers can be overcome by a mechanism of recovery. So, we are going to talk about recovery, but one point that I would like to make here is this competition between primary and the competition between strain hardening and recovery during the primary creep stage causes the evolution of a dislocation substructure, and this dislocation substructure evolves and then attains a constant state during the secondary stage of creep. So, what is very interesting is the correlation between the dislocation substructure and the strain rate of deformation. So, we said primary creep stage is a stage where the strain rate of deformation is constantly decreasing, and that is because of the rate of strain hardening being higher than the rate of recovery. During the decrease in strain rate, we are also seeing that a dislocation substructure is getting evolved, and when the rate of strain hardening is balanced by the rate of recovery, creep rate comes to a constant value. So, that is the minimum creep rate, and at that point what also happens is the dislocation substructure that was evolving till then now becomes constant, and it stays constant during the secondary stage of creep. So, since I have introduced the term called recovery, so I am going to talk a little bit about recovery in the next few slides. So, recovery is a stage of annealing. So, we know annealing is heating a material inside a furnace, heating a material at a high temperature, and annealing consists of 3 stages. You can have the first stage of annealing is recovery, the second stage of annealing is recrystallization, the third stage of annealing is grain growth. In the first stage of annealing, which is recovery, what happens is the physical and mechanical properties of a material start recovering. So, let us take the example of strength or hardness of a material. We know when the material is experiencing cold working or plastic deformation, the strength of the material is going to increase. The increase in strength is because of strain hardening. So, say hardness increased because of plastic deformation or cold working. Now, during recovery what happens is the hardness comes back to its original value, the value that the material had before it started experiencing plastic deformation. So, that original value is recovered. So, the properties basically are recovered during the recovery process. Now, recovery in a very simple sense is a result of annihilation of excess dislocations. So, the concept of annihilation comes into play because strain hardening happens because of the dislocations stopping each other from moving, and recovery helps the dislocations to move again, and that movement will happen only when dislocations start annihilating each other. The annihilation of excess dislocations can occur by the coming together of dislocation segments of opposite signs. So, if you have a positive edge dislocation versus a negative edge dislocation, and say if all these dislocations are trapped somehow, if these two dislocations can come together, then the positive and the negative dislocation can annihilate each other and restore the original structure. So, the annihilation can for the annihilation to happen, you need both the processes of slip and climb. That is because two dislocations of opposite sign, for them to come closer to each other, you need them to slip or glide on the slip plane, and then if they are on different slip planes, one of the dislocation could climb up into the other slip plane and then annihilate the dislocation of opposite sign. So, the annihilation process requires both glide and climb of dislocation. So, this is a very simple way of looking at the process of recovery. A slightly complicated form of recovery process is known as polygonization. So, polygonization is also again a result of recovery process of a strain hardened crystal. So, when you are plastically deforming a crystal, under certain circumstances these crystals can become bent. So, let us assume this is one grain or a crystal that is plastically bent, and when there is when the material has plastically bent, you will have dislocations forming within the material. So, these are all dislocations. So, say that is a lattice plane that is bent, you can have dislocations. The dislocations are the cause of the bending of the crystal. So, you will have a dislocation arrangement like that. Now, when this bent crystal is annealed, what happens is this bent crystal now breaks up into a number of closely related small perfect crystal segments. So, this bent crystal goes from that stage to this stage. So, where you had a continuous plane, lattice plane, is now it now takes the shape of a more segmented. If you see segments of the crystal. So, the curved crystal now breaks up into a number of closely related small perfect crystal segments. So, this is what happens during recovery. Crystal assumes a slightly newer shape, and this process is called polygonization. Now, what exactly happens here is the dislocations that were present along the curved plane, they start realigning themselves. So, the alignment of dislocations along definite arrays leads to the creation of low angle grain boundaries. So, what you see here is these are all dislocations that have started ordering themselves. So, the dislocations that were present randomly in this case, so dislocations that were present randomly along the slip plane have now started ordering themselves in certain arrays. So, they form some form of an array which looks like a wall. So, these arrays are known as low angle grain boundaries. So, the alignment of dislocations along definite arrays leads to the creation of low angle grain boundaries. What happens is when the dislocations start rearranging into these boundaries, that leads to the removal of the lattice curvature. So, the curvature that you saw is now removed, and the crystals lying between pair of low angle grain boundaries approach a state of strain free crystals. So, unlike the lattice plane where the dislocations were arranged randomly, when the dislocations start ordering themselves into definite arrays, the region between two definite arrays is free of dislocations, and that is why it becomes a strain free crystal. So, in the first case you had dislocations all along the lattice plane. In the second case, the dislocations started ordering themselves in certain arrays, and the region between two arrays is free of, this region is free of dislocations, and hence can be considered a strain free region. So, this rearrangement requires help of dislocation climb. So, the dislocations need to climb and move around for the rearrangement to happen, and that is why the process of polygonization can happen at only temperatures which encourage recovery. So, polygonization is a high temperature process, unlike normal recovery which can happen at low temperatures also. And these strain free crystals are also known as subgrains. So, the strain free crystals that you see, these strain free crystals are known as subgrains, and the low angle grain boundaries, the low angle boundaries are also called sub boundaries. So, these arrays, the array of dislocations are known as sub boundaries, and the region separated by two sub boundaries is known as a subgrain. An example of a subgrain and a subboundary is shown in this micrograph. This is a transmission electron micrograph of a titanium alloy crept at high temperature. And what comes out from this figure is the neat arrangement of dislocations. So, if you see, these are all dislocations that have arranged themselves in a very neat fashion. And if you look, so this is one array of dislocation, this is another array of dislocation. So, these are sub boundaries and the region separated, if you can see, it is free of any dislocations. So, it is a strain free region. So, these boundaries are sub boundaries and this is a subgrain.